Hi all, I am Ashik H, PhD student at ICTS Bangalore. Today I would like to briefly tell you about my work, Holography of Information in a Ball of Finite Radius. This is work done in collaboration with Navagadam, who is a postdoc at ICTS. Let me start by thanking the organizers of Strings 2025 Abu Dhabi for giving me this opportunity. So, in a quantum theory of gravity, information is stored in a way which is very different from what you see in a local QFT. And this is captured in the principle of holography of information, which states that in a quantum theory of gravity, information that is available in the bulk of a Cauchy slice is also available near its boundary. And this can be seen even in a low energy effective field theory description of gravity as the statement that an asymptotic observer at infinity can distinguish between two states in the bulk. Now, we would like to ask a question. What if the observer is not at boundary, the boundary, asymptotic boundary, but at some finite radius? More precisely, the question is information contained in a ball of finite radius holographic in nature? And we answer the question as yes, within the confines of linearized gravity approximation for low energy states. So more precisely, what is our setup? Our setup is we are in 3+1 dimensional asymptotic flat spacetime, and we couple scalar field theory minimally to gravity, and we work in the linearized gravity approximation. And in this approximation, the Wheeler-DeWitt equation or the Hamiltonian constraint becomes the statement that if you integrate the Hamiltonian density of scalar field on a ball of radius r, then that becomes equal to metric fluctuations at the boundary of the ball. Now you place a bulk observer and a boundary observer, and we would like to argue that whatever the bulk observer sees, the boundary observer will also see. And to have this statement in a clear way, we consider a basis of states which are like unitary excitations on top of vacuum. Given these set of states, can the bulk observer distinguish two different states? And what about the boundary observer? Can they distinguish between two such states and so on? These are the type of questions we would like to ask. And why unitary excitations? Because if you are in a local QFT, two states which differ by the action of a local unitary cannot be distinguished from each other by local measurements outside the light cone of the unitary. Now, the crux of our paper can be explained in this simple computation where you have a state psi as given in this equation. Now the question is, given states of this form, what can the bulk observer see and what can the boundary observer see? Now, uniquely identifying such a state is the same as extracting out the functions that define the state, namely f1, f2, f3, and so on. And we have shown that a set of correlators which will allow the bulk observer to extract out certain information about f1, f2, f3, and so on. And the same information can be extracted out by the boundary observer also by using a combination of h and pi and phi operators. For example, the bulk observer will get profile of the function f1 inside the ball, and the boundary observer will also get the same information. Similarly, for f2, f3, and so on, an analogous statement can be made. And the discussion can be generalized for more general unitaries. And in future, we would like to ask some interesting questions like what happens if excitations are on top of a black hole background, and is there a gauge invariant formulation, and so on. So for more details, have a look at our paper, and thanks for listening.